In the first video on discrete probability distributions, we had this particular case where uh, we looked at historical data and we were able to assign a probability of a certain number of computer network interruptions. Um, so, for example, we had this table where we 35% of the time in the past we had 0 and 25% of the time we had 1. And so having this table enabled us to do a few things. First, we were able to just get a probability of observing a certain value. So remember that the uppercase X is the symbol for the random variable. So in this case, the random variable is the number of network interruptions per day. And the lowercase x, and sometimes it's got this subscript I here, so this is I equals 1, 2, 3, 4, etc. So we were able to say, okay, so what's the probability that this random variable takes on the value of 2? And we were able to say, for example, so we had this function where we passed in, so okay, so the probability that x is equal to 2 is equal to 0.2. Okay, so that's one thing that it let us do that. And this particular thing where you have a function where you can get back a probability is called a probability mass function. So PMF for short. So the probability mass functions only actually exist for the discrete probability distributions. When we get into continuous distributions, we're going to have something else. But so for now, just know that a probability mass function lets us put in a certain outcome and get back a probability of that outcome. Okay, so in addition to the probability mass function, we were also able to find the expected value. So the expected value of x. Okay, so given what we've seen historically, what can we expect x to be? And so in this scenario, we use this as a kind of planning thing. So how much IT staff should we keep available? So how many can we expect? So how can we work our staff planning? And we were able to say, okay, in the general case, for any discrete probability distribution, if we take the probability, the output of the probability mass function for each of these outcomes, and then we multiply that by the value of that outcome. So let's say this is the probability times this, plus this times this, plus this times this. If we add all these up, then we're going to wind up with the expected value. Okay, and I think in this case it was something like 1.7. Okay, so the other thing we were able to do is to come up with a number for the variance. And what we did in this case, we also started with the probability mass function for each of the outcomes, and then multiplied it by the squared deviation of that outcome from the expected value, from the mean. So we said that the mean and expected value in this case are identical. And so we added up all the squared deviations times that probability, and that gave us a variance, which gives us some kind of notion of how predictable these outcomes actually are. Okay, so what we would like to do then is to not always have to rely on a table lookup for this thing. It would be nice if we had a situation where we had just a function. So remember from like high school algebra that what we mean by a function is we have some function of x, and that's going to give us a unique output. So you can think of a function as this machine, this bin where you're putting in some x, and then what you're getting out is some function of x. So it's like this transforming thing. Okay, so what this discrete probability distribution here is so this probability mass function is a way of putting in a particular x and then getting back a probability. So we can think of this function then, so it's a function from some integer values. Okay, so we've got these integer values, 0, 1, 2, 3, 4, 5, and it's mapping those integer values onto real values that are constrained to be between 0 and 1, because remember, probabilities range from 0 to 1. Okay, so what we would like to have for any situation is, rather than just looking it up this way, if we could, for example, ask questions like, okay, well, what's the probability of a certain value that we've never seen before? Assuming that we don't have collectively exhaustive cases over here. So we'd like to just have a nice general function that lets us put in an outcome and get back a probability of that outcome. Okay, so let's think about an easy case to start off with. So let's say I have a function that is a constant. Okay, so the simplest kinds of functions are the constant functions, where I just say, okay, so function of x, this particular function of x, is just some constant value. So let's just say it is 1/6. So f of x is equal to 1/6. Okay, so a nice easy function. So no matter what you put in there, so f of 2 is equal to 1/6. F of 4 is equal to 1/6. Okay, so if we think about this, and rewrite this function slightly so that it is, so the name of the function is p, and we put it in like this. So the probability that the random variable x takes on the value 3 is equal to 1/6. Probability that the random variable x takes on the value 4 is equal to 1/6. Okay, so not a terribly interesting function, but an easy one because it doesn't depend on x. It's always the same. And what we have in this case then is our old dice case. So we have what's called a uniform distribution, where all outcomes are equally likely. Okay, so the probability that x is going to be 3 is 1/6. Doesn't depend on x at all. It is constant across all outcomes. Okay, so if we were to represent this visually, we would have this rather uninteresting bar graph where every outcome is the same. Okay, so then the first thing we want to do, with a probability distribution is to have the probability mass function, right? So we can we already have that. That's pretty easy. It's always just 1/6. Okay, so we have our probability mass function. Then we can calculate for an arbitrary x that it's going to be equal to 1/6. Okay, so what about the expected value? What's the expected value of a uniform distribution? Okay, now this is something that we've already calculated. So last time we said, okay, well, what we would expect over the long haul would be the average. So we added up all of the outcomes. Let me just write this. Let me just start with a more basic. So we just added up all the outcomes: 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then we divided by 6. And then it turns out that average wound up being 3.5. Okay, so we could go over all of the possible outcomes and then add them up, and that would give us our average, so that would be our expected value. But there's actually a shortcut way for this. It turns out that you can get the expected value of a uniform distribution. So we'll say that x follows a uniform distribution between, we'll stick to our case, 1 and 6. It turns out that this is just n plus 1 over 2. Okay? So why would this average wind up being just this n plus 1 over 2? Okay, so let's see if we can figure out why that works out. So let's rewrite this to be a little bit more general and see if we can figure out how it turns out to be like this. So remember that what we have over the numerator really is we have the sum of all of our integers from 1 up to n, and well, this would actually be I. But let's just write it as x sub I. Okay, so we're adding up all of these x's, and then we are dividing them by 6. Well, 6 is n, so we can just put this over n, or we can bring it out here, so 1 over n. So we're multiplying 1 over n times the sum of all of these integers. Okay, so why is this the same as n plus 1 over 2? Okay, so what we have to do is figure out why this expression is equal to this expression. So I want to talk about kind of a legend in math of Carl Friedrich Gauss. Supposedly, and I'll just write this down over here. Supposedly, when he was pretty young, Carl Friedrich Gauss, and that says Gauss, not Gruss, was he was a mathematical genius from a very young age, and to keep him busy, supposedly, somebody told him to add up all the numbers from 1 to 100, and he said, well, that's not, being Gauss, he was not going to do it the tedious way. He was going to figure out a better way. So what he realized was that he just started writing the numbers down like this. And, you go all the way out to 100, but in our case, we'll just stick to 6 here. And then we could add all these up, or let's just reverse the numbers and see what happens. So let's write the numbers again, but we'll start from here. So we're counting down. So it'd be, 6, 5, 4, 3, 2, and 1. Okay. Now let's add them this way. So we've got 7, 7, 7, 7, 7, and 7. Okay, so now instead of having an addition problem, we have a multiplication problem, which is much quicker. So it turns out that there are how many? There are 6 7s. So we got, we know that this is going to be equal to 6 times 7. But there's a little bit of a trick here, because we're not adding up just these numbers, we're adding up those numbers twice. So if we just divide by 2, then we get our actual number. So it turns out that the sum of these first 6 integers is just going to be 6 times 7 over 2. Okay, so 21. But let's go ahead and generalize this, try to figure out, well, how do we turn this into a formula? Well, the 6, what was 6? Well, 6 just turned out to be n. And then this 7 just comes from the fact that, we're adding this way, we're turning this first 6 into a 7. So we're multiplying, we wound up multiplying it by n. So these, remember, n is 6, so these wound up being all 7s, so these were all n plus 1s, n plus 1 over 2. So n times n plus 1 over 2. Okay, so if we look back over here, what we're trying to do is sum up these integers. So then this whole expression, if we realize that this is just the sum of all the numbers from 1 up to n, then we can do this. Okay, so we carry over our 1 over n, and then what are we multiplying it by? This. Okay, so n plus 1 over 2, and remember that this was actually multiplied by n. Okay, so then these n's cancel, and we wind up with n plus 1 over 2. Okay, so the expected value then of a uniform discrete distribution is going to be equal to n plus 1 over 2. Okay, that gives us a nice shortcut. So remember, when we did it this way, we figured out that it was 3.5. This gives us a nice shortcut. So we have n is equal to 6, plus 5 is 7 over 2. So this was 7 over 2, which equals 3.5. Okay, so there's a simple case of a distribution that allows us to come up with a function that maps an individual outcome to a probability, and in addition to giving us the PMF, we also have a way of getting the expected value, and also the variance. We're not going to go over that right now. Okay, so as we go forward, we're going to be looking at these probability distributions, and they're going to allow us to come up with the mapping from the outcome to the probability, and then also certain characteristics such as the expected value and the variance. In every case, we're going to talk about the expected value, and we're only going to look at the variance in a couple of special cases. Okay, so let's think about this. When we try to come up with a probability distribution, we have to think about how the data is actually generated. And we're going to look at a particular distribution that comes from cases like these. Okay, so what is the probability that a basketball player, that is basketball player A, will make 6 baskets? Okay, let's think about what additional information we need to have in order to answer this question. So we can just say, okay, well, we're looking for 6. So let's just say, if we know that we're trying to form a probability mass function here, that we're interested in 6. So we'll go ahead and call that x. So x is going to be, let me stick to my color scheme here. So x is going to be equal to 6. So we're looking for 6. Well, what else do we need to know? Obviously, we don't have enough information here. So what other pieces of information will help us answer this question? Well, obviously, we need to know how many baskets he's trying, right? I mean, if he's only trying 6, then it might be low. If he's going to try 100, then the chances are very high that he's going to make 6. So we're going to need to know the total number of attempts that he makes. So we'll call that n. N is always a good number to use for a count of something, for your total individual trials. So we've got n, and we don't know what this is. Okay, it's not given in the problem. But what else do we need to know? Is that enough? Well, in addition to knowing how many, and how many we're looking for, we're also going to need to know something else. That is, how good is the player? Okay, and that will be embodied in the probability that he or she will make an individual basket. So each attempt at a basket is a trial. We'll call that a trial. Okay, if we think of that as a trial, And n is the number of trials. And then also for each trial, we want to know what's the probability of success. So we have this idea of a trial, and we want to know about the success, number of successes. So we're looking at 6 successes in a certain number of trials and a certain probability of success in each trial. Okay, so this will be the probability of success. Okay, so let's just go ahead and put in some hypothetical numbers here, just to see, just to start actually calculating this. Let's say that the number of trials is going to be equal to 10. They're going to try 10 times, and let's see, how good is the player? Well, we'll say that their probability of success, historically, they've made 70% of the shots. We'll ignore any variations such as the distance from the basket and all that. We're just going to say that their historical probability of success has been 70%. They're going to try 10 times, and we want to know what's the probability that they're going to make 6 baskets. Okay. So how would we go about solving this? Okay, so we've got these 3 pieces of information. Let's go ahead and think about how we might, before we go and look at a formula, let's just think about how we might go about solving this. So I'm going to give myself a little more room here. Okay, so remember that we had x, we had n, and we had pi. And x was going to be, this is the number that we're asking about. So we're interested in the number of successes. N is the number of trials. And P is the probability of success in each trial. Okay, well, let's think about, we've been using the same approach for some other problems where we thought of each trial as a slot that we can fill. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so each of these is one of those shots, and we want to know, well, let's say for our case, we were looking for 6, and the number of trials was 10, okay, and the probability was 0.7. Okay, so let's say we've got 10 trials here, and we want to know probability of 6 successes. Well, let's just think about if we were to take the first 6, 1, 2, 3, 4, 5, 6, and let's just say, okay, having the first 6 baskets a success, and then the next 4 a failure, that is, they miss. If we apply the general multiplication rule to this case, then we can say, okay, well, the probability of each one of these is 0.7, so the probability of having all 6 is going to just be the 0.7 times 0.7 times 0.7. So we can say this is pi. And that's going to be pi, and that's going to be pi. So we're just going to be multiplying all these pi's together. Now remember, this is not 3.14. This is it's a little bit of a misleading denotation here, but just know that this pi doesn't stand for pi as you normally know it. This is the probability of success. So it's just, we could use p also, and in some texts you'll see that. So we're going to have pi times pi times pi times pi. So this is going to be pi, so the probability of success raised to the 6th power, times, and then these are these are all the failures, right? So what's the probability of failure? Well, if the probability of success is 0.7, then the probability of failure is 0.3, right? So and that's just 1 minus pi, right? So because there's only two possible outcomes here, success or failure. So each one of these then is going to be a 1 minus pi, okay? And now there's 4 of them. So we had 1 minus pi to the 4th. And so just to generalize it a bit, these superscripts up here, where did this come from? Well, this 6 was our x, so we'll say this was pi to the x. Okay, and so to generalize this part then, we had 1 minus pi to the 4th, and 4 came from, this was the number of failures, right? So if we had 6 successes and we had 10 trials, then this is, the number of failures is going to be n minus x. So total number of trials minus the number of successes is the failures, obviously. Okay, so we got pi to the x times 1 minus pi to the n minus x. Okay, so this is a good start. So this gives us the probability of this case where they have successes on the first 6 trials and then failures on the next 4. So that's the probability of that. But this is not the only way to get 6 successes. It could have been the last 6, or it could have been this one and this one and this one, etc. So there's a certain, there are more ways of getting this, and so this should be familiar then. So what we have to do then is to figure out, well, how many different ways are there to have 6 successes in 10 trials? How many different ways? So this is actually what we've seen before. So we're doing 10, choose 6. Or we wrote it sometimes this way, 10, choose 6. So how many different ways are there to choose one of these slots and put choose 6 of these slots to put S's in for success, okay? And remember the formula for, so the formula for, this is a combination. Formula for the combination was n factorial divided by x factorial n minus x factorial. Okay, so we've been through that one before. So we're going to have one of these for each of the possible arrangements, not arrangements, for each possible selection of 6 successes. So putting it all together then, we're going to say, okay, so the probability, and x is our random variable, which is going to denote the number of successes. So the probability that x is going to take on a particular x, and because we have these other parameters that go into this, we're going to use that conditional probability notation and say given a certain number of trials and a certain probability of success is going to be n choose x, so n factorial divided by x factorial n minus x factorial times what we figured out up here, pi to the x, 1 minus pi to the n minus x. Okay, and so this is the total, the complete formal definition of how we solve this right here. Okay, and this is called the binomial distribution. And this in particular is the probability mass function. The terminology that your calculator uses is slightly different, and I'll go over that in a little while. Okay, but just to just to show you what it looks like. So on the slides and in your book, it presents it to you this way. And so now this shouldn't seem terribly intimidating. So then we got our random variable, our particular variable. This was our number of trials, our probability of success. This is our conditional probability notation. This expression here, sorry, that should include that exclamation point there. This was just n choose x, lowercase x, and then this is the counting up the successes, and this is counting up the failures. Okay, so this is how you use this. Now, one thing I want to emphasize as we look at the next problem is that this allows you to find the probability of getting a particular number. So the probability of exactly 9 baskets, or the probability of exactly 6 baskets. So we're going to look in a minute at probabilities of certain ranges. But for now, let's just be aware that we have a tool here to find one particular value. Okay, so here's an example problem. Let's in a minute, go ahead and pause the video to see if you can figure this out. So we got a software development project that has 10 separate tasks that needed to be completed on time. If the probability of each project being completed on time is 0.8, what's the probability that exactly 9 will be completed on time? Okay, so hopefully you've had some time to take a look at this. So we're dealing with a binomial distribution problem here. You know, the key terms to notice is you should be looking for trials. You know, this idea that there are these trials and that you're interested in the number of successes, and that's a dead giveaway that you're dealing with a binomial distribution problem. So we can think of each of these 10 separate tasks as a trial. So we've got 10 trials. So we can say, okay, well, we already know that n is going to be equal to 10. And if the probability of each project being completed on time is 0.8, so there's our probability. So we know our pi is 0.8. And what's the probability that exactly 9 will be completed on time? So that's what we're asking about. So we're looking at the case where x is equal to 9. Okay, so I'm going to go ahead and write this down. So remember that the binomial formula gave us, you know, given n and pi is going to be equal to n choose x, so n factorial over x factorial n minus x factorial, factorial, and this is going to be the successes, which will be pi to the x, and then the failures 1 minus pi to the n minus x. Okay, so now we can solve this just by plugging these values in. I'm going to show you how to also do it the shortcut way in both Excel and on your calculators, but let's go ahead and do this at least one time through. So this will be 10 factorial divided by 9 factorial, and then n minus x, so it's just going to be 1 factorial, which is just 1. So pi is 0.8, and then x is 9, and then 1 minus pi is going to be 0.2, and then n minus x, so 10 minus 9 is just 1. Okay, so we can expand this to help us do some cancellation. So 10 times 9 factorial, 9 factorial, we'll just ignore that. So that it's just going to be 10 times 0.8 to the 9th times 0.2 to the 1st. And let's go ahead and do it in the calculator here. I don't know what the answer is, so we'll do 10 times 0.8 to the 9th. And we can just plug it right in and not have to worry, because the order of operations will give us the right answer here. The first thing it will do is, do this 0.8 to the 9th, and then it will multiply left to right. So 10 times 0.8 to the 9th times 0.2 to the 1st is just 0.2. So we'll put this in. Okay, so that's going to be 0.268. 0.268. Okay, and so let's remember what this is telling us. This is the probability that we're going to have exactly 9 successes given these parameters. Okay, so we have about a 1 in 4 chance of exactly 9 being completed, and so you should think, well, does that really make sense? And it does make sense to have a small number here, because we're looking at the case where it's exactly 9. The probability of there being exactly 9, even if the probability is high here, so it's the probability of success for each project is pretty high. So the probability that you'll have a lot is high, but the probability that you'll have exactly 9 isn't necessarily all that high. Okay, so just to emphasize then, so to review the formula, this binomial distribution formula gives you the exact value. So you're looking for the probability that x takes on an exact x. Okay, but if we think about what we generally do in the real world, then we're not always necessarily interested in the probability that x is going to be exactly some particular x. We're more interested in whether x is going to be less than or equal to a certain value or greater than a certain value. So here's some business cases where you're asking a question about less than or equal to. So say, what's the probability that this job run, so this will be some kind of manufacturing, will produce 5 or more defective products? So this is going to be probability that x is going to be greater than or equal to 5. And what's the probability that 2 or more machines will be broken after 20 runs? So once again, we're looking at probability that x is going to be greater than or equal to 2, and the probability that 100 or more people will respond to a promotional flyer sent to 5,000. So we can see that these are all binomial questions, but we're not dealing with an exact value. So we're looking for the probability that x is going to be greater than or equal to 100. And then here, probability 3 or more light bulbs will burn out after 100 hours of lighting. So probability x is greater than or equal to 3. Okay, so if we think about this initial example discrete probability distribution, we can get a sense of how we go about calculating these. So for example, so we know the probability that, let's say, it's equal to 2 is going to be, it's going to be 0.2. But what's the probability that it's going to be, that x is going to be, let's say, less than or equal to 2? Well, there are only 3 cases to deal with here, right? Less than or equal to 2 means it's going to be 0, 1, or 2. So we could just add all these up. So this is going to be 0.8. Is that right? So 6, 7, 8. Yeah, so 0.8. So if we just add all of these up, we can get that the probability that it's going to be less than or equal to 2. Okay. Now, what if we were interested in, let's say the probability that it's going to be greater than 3? Well, there's a few ways to do this, or two ways to do this, but we can add. So the only cases where it's greater than 3 are these 2. So we can add these up and we'll see that it is just 0.1. Or we can also do, because we know that these add up to 1, it'll just be 1 minus the probability that x is going to be less than or equal to 3, right? So it turns out that when we're trying to solve a case like instead of trying to find an exact that there are exactly a certain number of successes, that we want to know whether there are less than or equal to or greater than a certain number of successes, then we no longer are using that formula that I showed you before, because that's our probability mass function or probability density function. Instead of just using a particular, we're just trying to find a particular value, we're interested in some kind of accumulated value. We're interested in cumulative. Some notion that we're going to be adding up a bunch of values. Now, rather than go and show you the Cdf, the cumulative distribution function of the binomial formula, I'm just going to make you aware that it is available to you, and I'm going to show you how to solve. I'm going to show you the difference between these two ways of solving, the exact and the cumulative. Okay, so if we go back to our example here, we were looking for exactly 9 successes, and we calculated it manually on the calculator, and we wound up with this answer down here just by actually plugging the numbers into the formula. Okay, oh, that's hard to read. Okay, but we can also use the distributions that come with your calculators. It knows how to do this, and all you have to do is put in n, x, and pi. So if we come here and push second, and then go over here to distr, and then come down to the, so we've got 2 there, Binomial Pdf and Binomial Cdf. For this case, we're going to use the PDF, so binomial probability density function. And so we'll do that one when we're trying to find out an exact value, probability of exactly 9, for example. So we'll hit enter. So how many trials? We had 10 trials. And the probability of success on an individual trial was 0.8. And the value that we're asking for here is 9. And then we just hit enter twice, and we got the same answer, 0.268. Okay, so that's how we figured that out on the TI-84. We could also do it in Excel. So in Excel, I'm just going to set up the parameters here. So we had 10 trials, that's our n. Our probability of success was 0.8. And our x, that is the number of successes, was 9. Okay, now I could just execute this, figure it out piecemeal like we did before, but like the calculator, Excel has a way to calculate binomial probabilities, and it's just binom.dist. Okay, and so notice that the little prompt here gives us a clue as to which parameter we put in. So this is number of successes. So the number of successes was 9. The number of trials, which was 10. Actually, let me just go ahead and select the cell. So the number of successes was there. The number of trials was there. And this probability underscore s is the probability of success. It's just going to be there. And now notice that it says cumulative. So because we're asking about an exact value, we want to know exactly 9, we're going to say false here. And we get 0.268, which was the same as we had before. Okay, so let's look at the same problem then and solve it using the calculator in Excel. But now we're going to look at the case where we want to know what is the probability of 9 or fewer. Okay, so not exactly 9, 9 or fewer. Okay, so it's the same, we've got the same n, we've got the same pi, and this time we've got 9 or fewer. So we need to take advantage of this CDF, cumulative distribution function, so binomial CDF. So we'll solve this on the TI-84 first. Okay, so binomial CDF. Okay, so now we put these parameters in. So there's where we did the binomial PDF. Okay, so now we access it the same way. So second, distributions, normal CDF this time. So cumulative distribution function. Okay, and so, oh, sorry. Sorry, not the normal. This is the binomial. So let me exit out of there. So the distribution, binomial CDF. So now we have number of trials is 10 again. Hit enter. Probability 0.8. And the x value we're asking about is 9. Okay, so this is going to give us the probability of 9 or fewer. So the probability that x is less than or equal to 9. So hit enter twice. And it tells us that that probability is 0.893. Okay, so 0.893. So notice how high it is. So the reason for this is because the probability of success is 0.8. So the probability of having anywhere from 1 to 9 is pretty high. And the probability of, so it's going to be a lot higher than the probability of having exactly 9. Okay, so if we were going to do the same problem on Excel, we would use the same function that we used before, but the difference would be that we would put in a true here. So let's go ahead and do that. So this will be our our binomial PDF, and we'll put the CDF here. So we'll say binom dist. Okay, so once again, number of successes 9, number of trials 10, probability of success 8, and this time we're going to put in true for cumulative. And we've got 0.893, same as before. Okay. Okay, so just remember that when you're doing either the calculator or Excel, that this is always going to be giving you the probability that x is less than or equal to this x that you're putting in here. So in this case, this 9. Okay, so what if we were interested in, for example, the probability that x is greater than a certain value of x? So let's say we're interested in this case, the probability that x is going to be greater than 9. Well, in this case, there's two ways to do that. There's only one other case, that is all 10 succeed. So we could just do binomial PDF of 10. Or, so that would give you, the only case where x would be greater than 9 is if it's 10, so that would give you that probability. Or another way of doing this would just be to do 1 minus the probability that x is going to be less than or equal to 9, which is what we calculated over here. So it would just be 1 minus this number. Okay. All right. So we went over the binomial distribution, how it gives you a way to get a probability mass function, sometimes called a probability distribution function. And so we looked at the uniform distribution and how its probability mass function is nothing other than a constant. And we went over how to how to find a particular value of x under the binomial distribution, as well as a cumulative value for cases where you're looking for less than or equal to. So one more thing that I want to say about the binomial distribution is to think about what would its expected value be. So what would the expected value up here be? So given that we have 10 separate tasks and our probability is 0.8, what number would you expect to see succeed? Well, let's think about it. So that would mean that, if 80 out of 100 succeed, that would mean that 8 out of the 10 would succeed, right? So the expected value then here would be, the 10 trials times the 0.8, so we would expect 8. Okay, so let's think about another situation. If we only had a 50-50 chance of being on time, that would mean that pi would be 0.5. So if we had 10 and we only had a 50-50 chance, then how many would we expect? How many would we expect to be completed on time? Well, okay, so half of 10. So once again, we've got 10 times 0.5, which would be equal to 5. So the expected value of a binomial distribution then is just going to be n times pi. So you just multiply the number of trials times the probability of success for each trial, and that's going to give you your expected number of successes. Okay? All right, hope that helps, and let me know if you have any questions.